Download this code from codegive.com, link in the description below. Deadlock detection and recovery in operating systems, a deep dive. Deadlock is a critical issue in operating systems that occurs when two or more processes are blocked indefinitely, waiting for each other to release resources that they need. This situation can paralyze a system, preventing any of the involved processes from progressing. Understanding deadlock detection and recovery is essential for designing robust and reliable operating systems. This tutorial will provide a comprehensive explanation of deadlock detection and recovery, covering the following aspects. 1. What is deadlock? 2. Conditions for deadlock * the Coffman conditions. 3. Deadlock detection techniques *. Resource allocation graph, RAG, for single instance resources. Banker's algorithm, for general resources but more of a prevention algorithm. Deadlock detection algorithm, for general resources. 4. Deadlock recovery strategies *. Process termination. Resource preemption. 5. Code examples, C/C++, illustrating deadlock detection and recovery mechanisms. 6. Considerations and challenges. 1. What is deadlock? Deadlock is a situation where two or more processes are blocked forever, waiting for each other to release resources. Imagine two cars approaching an intersection. Each car needs to proceed straight, but each is blocking the other. Neither car can move until the other moves, resulting in a deadlock. Example *. Process A holds resource R1 and requests resource R2. Process B holds resource R2 and requests resource R1. Process A cannot proceed until it gets R2, which is held by B. Process B cannot proceed until it gets R1, which is held by A. A deadlock has occurred. 2. Conditions for deadlock, the Coffman conditions. Deadlock can only occur if all four of the following conditions, known as the Coffman conditions, hold simultaneously. Mutual exclusion. Resources are non-shareable. Only one process can use a resource at a time. Example: a printer, a critical section of memory. Hold and wait. A process is holding at least one resource and is waiting to acquire additional resources held by other processes. No preemption. Resources cannot be forcibly taken away from a process. A resource can only be released voluntarily by the process holding it. Circular wait. A set of processes P0, P1, Pn exists such that P0 is waiting for a resource held by P1, P1 is waiting for a resource held by P2, Pn1 is waiting for a resource held by Pn, and Pn is waiting for a resource held by P0. This forms a circular dependency. 3. Deadlock detection techniques. Deadlock detection aims to identify whether a deadlock has actually occurred in the system. Several techniques can be used. A. Resource allocation graph, RAG, for single instance resources. The resource allocation graph, RAG, is a directed graph that visually represents the allocation of resources to processes. It consists of processes represented by circles. Resources represented by squares. Request edges. An edge from a process to a resource indicates that the process is requesting that resource. Allocation edges. An edge from a resource to a process indicates that the resource is allocated to that process. Deadlock detection. If the RAG contains a cycle, then a deadlock exists. Example Let's say we have two processes P1 and P2, and two single instance resources R1 and R2. P1 is holding R1 and requesting R2. Asterisk P2 is holding R2 and requesting R1. The RAG would have the following elements. Asterisk nodes, P1, P2, R1, R2. Asterisk edges. Asterisk R1-P1, R1 is allocated to P1. Asterisk P1-R2, P1 is requesting R2. Asterisk R2-P2, R2 is allocated to P2. Asterisk P2-R1, P2 is requesting R1. This graph contains a cycle, P1-R2-P2-R1-P1. Therefore, a deadlock exists. Limitations. RAGs are only effective when dealing with single instances of each resource type. B. Banker's algorithm, deadlock prevention, related, but not detection. While the Banker's algorithm is primarily a deadlock avoidance technique, understanding it helps to appreciate the complexity of resource allocation in a multi-process environment. It is not strictly a detection algorithm but rather a preventive measure. The Banker's algorithm requires the operating system to know in advance the maximum resource requirements of each process. It then dynamically allocates resources to processes in such a way that a deadlock can never occur. It maintains the following information. Asterisk available asterisk a vector of length m indicating the number of available resources of each type. Asterisk max asterisk an nxm matrix defining the maximum demand of each process. Max I, J represents the maximum number of instances of resource type J that process I may request. Asterisk allocation asterisk an nxm matrix defining the number of resources of each type currently allocated to each process. Allocation I, J represents the number of instances of resource type J that are currently allocated to process I. Asterisk need asterisk an nxm matrix defining the remaining resource need of each process. Need I, J equals max I, J, allocation I, J. The algorithm determines whether a system is in a safe state. A safe state is one where there exists a sequence of processes such that all processes can finish their execution without causing a deadlock. If the system is in a safe state, a process can be granted a resource request. If the system is in an unsafe state, the request is denied to prevent a potential deadlock. C. Deadlock detection algorithm, for general resources. This algorithm is used when resources have multiple instances. It is typically more complex than analyzing a resource allocation graph. The algorithm uses the following data structures. Asterisk available, a vector of length m, representing the number of available instances of each resource type. Asterisk allocation, an nxm matrix, where allocation ij represents the number of instances of resource type j allocated to process I. Asterisk request, an nxm matrix, where request ij represents the number of instances of resource type j that process I is requesting. The algorithm works as follows. 1. Initialization asterisk. Asterisk work, a vector of length m, initialized to available. Asterisk finish, a vector of length n, initialized to false for all processes. 2. Find a process p_i such that asterisk finish I equals false. Asterisk request I equals work, i.e., the process's request can be satisfied with the available resources. If no such process exists, go to step 4. 3. Simulate the process finishing asterisk. Asterisk work equals work plus allocation _I. Asterisk finish I equals true. Asterisk go back to step 2. 4. Check for deadlock asterisk. Asterisk if finish I equals false for any process p_i, then p_i is part of a deadlock. 4. Deadlock recovery strategies. If deadlock is detected, the operating system must take action to break the deadlock and allow processes to continue execution. Common recovery strategies include: A. Process termination asterisk. This is the simplest, but often the most drastic, recovery method. Asterisk abort all deadlocked processes asterisk. This is guaranteed to break the deadlock but can result in significant data loss and wasted computation. Asterisk abort one process at a time until the deadlock cycle is broken asterisk. This is a more selective approach. The choice of which process to abort is based on several factors. Asterisk priority of the process. Lower priority processes are often chosen first. Asterisk CPU time used by the process. Processes that have used less CPU time might be selected. Asterisk resources held by the process. Processes holding resources that many other processes need might be targeted. Asterisk amount of work needed for the process to complete. Aborting a process that is close to completion can be wasteful. B. Resource preemption asterisk. This involves temporarily taking resources away from one or more deadlocked processes and allocating them to other processes to break the deadlock. This is only possible if the resource can be safely preempted. Factors to consider when selecting a victim process. Asterisk minimizing cost asterisk. The process chosen should be the one that will incur the least amount of cost, example rollback, data loss, due to preemption. Asterisk number of resources held asterisk. Select a process holding fewer resources. Asterisk priority asterisk. Select a lower priority process. Asterisk rollback asterisk. If a process's state can be easily rolled back to a safe point, it is a good candidate. Issues with resource preemption. Asterisk selecting a victim asterisk. Choosing the right victim is critical to minimize the negative impact. Asterisk rollback asterisk. If the process needs to be rolled back to a previous state, this can be complex and time-consuming. Asterisk starvation asterisk. If the same process is repeatedly chosen as a victim, it can lead to starvation, where the process never gets to complete its execution. 5. Code examples, C/C++. Here's a simplified example illustrating deadlock detection algorithm, assuming single instance resources for simplicity's sake, and process termination as a recovery strategy. This example is designed for conceptual understanding and would need to be significantly expanded for a real-world OS. Explanation asterisk. 1. Detect deadlock function asterisk. Asterisk. This function implements the deadlock detection algorithm as described earlier. Asterisk. It uses available, allocation, and request matrices. Asterisk. It returns true if a deadlock is detected and fills the deadlocked processes vector with the indices of the deadlocked processes. 2. Recover from deadlock function asterisk. Asterisk. This function demonstrates a simple recovery strategy, terminating all deadlocked processes. Asterisk. It iterates through the deadlocked processes vector and releases the resources held by each terminated process, updating the available vector and setting the corresponding entries in the allocation and request matrices to 0. 3. Main function asterisk. Asterisk sets up the initial available, allocation, and request matrices representing the system state. Asterisk calls the detect deadlock function. Asterisk. If a deadlock is detected, it calls the recover from deadlock function to resolve it. Asterisk prints the updated system state after the recovery. Important considerations for real-world implementation asterisk. Asterisk resource locking asterisk. In real systems, resources are protected by locks, example mutexes, semaphores. The deadlock detection algorithm would need to be integrated with the locking mechanism. Asterisk periodic detection asterisk. Deadlock detection can be computationally expensive, so it's usually performed periodically rather than continuously. The frequency depends on the system's criticality and resource contention. Choice of victim. Selecting the right victim for preemption or termination is crucial. A good strategy should consider factors like process priority, resource usage, and the cost of rollback. Complexity. Deadlock detection and recovery can add significant complexity to the operating system. 6. Considerations and challenges. Overhead. Deadlock detection and recovery mechanisms introduce overhead in terms of computation and memory usage. The detection algorithm must be efficient to avoid performance degradation. The recovery process, especially preemption, can be complex. Frequency of detection. How often should the deadlock detection algorithm be run? A trade-off exists between detecting deadlocks quickly and minimizing the performance impact of the detection process. False positives. In some cases, the deadlock detection algorithm might report a deadlock even though one doesn't exist, a false positive. This can lead to unnecessary process termination or resource preemption. Starvation. Repeatedly preempting resources from the same process can lead to starvation. Mechanisms should be implemented to prevent starvation. Integration with resource management. Deadlock detection and recovery must be tightly integrated with the operating system's resource management system. Distributed systems. Deadlock detection and recovery in distributed systems is significantly more complex due to the lack of global state information and the possibility of communication delays. Conclusion. Deadlock detection and recovery are crucial aspects of operating system design. Understanding the causes of deadlock, the various detection techniques, and the recovery strategies allows developers to build more robust and reliable systems. While the code examples provided offer a basic understanding, real-world implementations are significantly more complex and require careful consideration of performance, overhead, and the specific requirements of the system. Choosing the right balance between prevention, avoidance, detection, and recovery is key to creating a stable and efficient operating environment.